Hello everyone, welcome back to Codynamics. In this video, we will learn how to do basic meshing on an F1 car using cfMesh. Before we get into the tutorial, this video is sponsored by Protopre, which is a Formula 1 based board game that engages in an immersive racing experience. We are sure all the young Formula 1 fans are going to love this. The game is available in Amazon and the link is given in the description. If you might be interested in the game, you can purchase through that link. Now let's get back to the tutorial. This is the geometry that we are going to mesh in this tutorial. So this geometry was downloaded from the website Fetch CFD. So if you are interested in downloading any other CFD related models, you can check their website. It's free to download. And this model is also from the same website. Now this is a .stl file, which means this has only surface information. So if you go inside, it's all hollow. And this is what is suitable for your open form meshing, be it Snappy or cfMesh. You can also use OBJ format, but mostly when you download from online, you will be getting .stl files, and we have one now. Now we will start looking at the procedure for creating the case to do just the meshing. We will not be running the case in this video. Maybe in a future video we will do it, but in this tutorial we will just look at the procedure for the mesh. Okay, now I have a folder in which I have this .stl file. Now I have to create a folder called system. Okay, and this system folder is going to have all my OpenFOAM related files. So before we do anything, I will open my WSL in this location. Okay, now I'm just going to create a paraview file. Okay, yes, it's created. So the command to get started with preparing the geometry is surface feature edges. Now this command will take this STL file and then convert it into a format called .fms. So before I run it, I'll just try to run the help. Okay, so you see it takes certain options. So the options are like this, and one such option is the angle. So this angle is called the feature edges angle. I will talk about that in quite some time. And then we have to give the input stl file name and then the output file name. So if I start doing that, let's say my angle, for now let's keep it as 45. I'll explain how to arrive at that angle, but for now let's keep it as 45. And then the input file name, which is the formula.stl, and that's the file name I have. And let's say my output is formula.fms. Okay, this fms is mandatory. Now when I type enter, we will get this fms file. Now there is a slight problem in this. I will explain. The number one thing is like we don't know whether our feature edges is correct or not. So first let's talk about that. To understand what the feature edge is, you have to first click on this filter, search, and then type feature edges, and then click on apply. Okay, now whatever lines you are seeing is split based on angle between those two surfaces. So we can control this angle. Let's say in the left panel, if you see, we have something called feature angle. If I put 45 and apply, you can see less number of lines appear because there will be less number of places where there is 45 degrees between those two surfaces. Now when I go for 60, you can see even less lines. Similarly, if I put 85, say even less angles. So these are the angles that will be considered as a feature. So when I put 60, I think it captures everything necessary, but not too much. Like you can see these curvatures, and even on these planes, the rear wing, also in the wheels, you can see. So everything is almost getting captured. But if you do want to take more angles or more inclusiveness, then you can go for 45. But I think it is quite messy here and there. So in my opinion, this 60 is good for this geometry. But if you think that you can go for another angle for your geometry, then you can go. There is no rule that you have to use 60 only. So now we are going to do the same thing with 60. Okay. Okay, now we got the FMS file, which is based on our 60-degree angle. So this is just capturing all the feature edges and then storing it inside this FMS file. Now the thing is we have to create an enclosure around this, right? So to create the enclosure we have to create some STL that will act like inlet, outlet, top, bottom, front and back. So there are many methods to do that. I prefer using block mesh for it. So the first thing that we are going to do is go inside our system folder and then maybe copy some block mesh template from any case and then paste it. And now let me open it in my Visual Studio Code. Okay, now if you see we have the block mesh here and I chose all the points in such a way that it will enclose this car in a way that it will act like a tunnel. Okay, but if I go here and run this block mesh, it's going to give an error. Okay, so first we have to understand that we always need control dict if we scheme an FP solution even to run block mesh. So I will also copy that from any case. It doesn't matter what is there inside your FP scheme, FP solution or control dict just for meshing. So you can just copy that and then run the block mesh. Now we got it. But you see the end cells is just one. Now I will explain why I did that and how I did that. So if I go to my para.foam here and then go to surface wireframe, you can see this is the enclosure that we have and it has only one cell. So how I did is if you go here and in the divisions you can just put 1 1 1. Now these points are chosen in such a way that this enclosure will be created and we are just keeping one cell because that is enough for a cfMesh to work. And similarly I have also created the boundary faces. You can see I have inlet, which is this, and then we have the outlet, which is the back side, and then we have the top wall, and then we have the left and right, and also we have the bottom wall, which is below the car. Okay, now we will again go back to internal mesh. Now because of that we have only one cell. Even if you go to surface with edges you will be able to just see one cell. Now this is sufficient for cf mesh. Now the procedure is foam to surface. So when you do this, what will happen is it will take in your block mesh and then it will convert it into STL file. So we have to give a STL file name. So let's choose boundary.stl and I give that it is writing boundary.stl. Okay, so it is available here. If I open this STL, you can see that each of the surface has different color based on the STL solid labeling, and inside this we have our core, which is this STL. Okay, now what I'm going to do is like I'm going to merge both of them. Like if you just go inside this STL, there is no uh, car inside, so we have to merge it. But before we merge it there is a caution. Like if you have an STL and if you open it in VS Code, if you are not able to see what is inside, then probably your STL is in binary. Now this method will not work on binary STLs, so you can use something like Blender or FreeCAD or any CAD modeling software to convert your STL from binary to ASCII. So once you do that you will be able to use it here. So you can check my other video where I have explained how to convert any STL from binary to ASCII. So you can follow that method. Now I will assume that you have the ASCII STL. So now we have two ASCII STLs. One is our formula.stl and the boundary.stl. So both are in ASCII. So I am able to read them in VS Code, which means it is in ASCII. Okay. Now if you see this boundary.stl, you can see that it says top wall and solid top wall and solid outlet and solid outlet, similarly inlet and then left and right. So this is how an STL is stored. It takes the vertices and then it creates faces. So a pair of three vertices will make one face, which is a triangle, and then it will form the normal face normal to say which face it is representing, and then it will form the whole STL. That's how it is made. Similarly, we also have the formula.stl. Now we can close these two. Now we want to merge these two. Okay, so what I'm going to do is like first type cat, which is for concatenate, and then formula.stl, and then you can type boundary.stl, and then let's just call it. Then you have to put this sign, which means whatever is coming out of it will be saved as an output. So before we look at this, let's just type this and enter. You will be able to see that it just prints the entire file here. But first the formula will be printed and then the boundary.html will be printed. So this command will give you whatever was printed inside a file. So for an example, if I just type this and then say log, then whatever came here will be inside a log file. So whatever was printed will be inside a log file. So we are going to use this method to manipulate it to create an STL file. So I'm just going to create a geometry.stl. Okay. Now it created geometry.stl. If I open this geometry.stl in our paraview, and if I go inside, you can see that car is part of the geometry now. Even if you go to wireframe, you will be able to see the car inside your boundary. Okay, now we can go to surface again. Let's clear this up. Okay, now this geometry is what we are going to work with for creating the mesh. So in the surface feature edges, I'm going to use geometry.stl to create my formula.fms. So I press enter, it created formula.fms again. So you can see the time, yes, it's created again. Now this will contain both our boundary as well as geometry. So if you open it inside your VS Code, you will be able to see that there is a formula, there is top wall, outlet, inlet, left and right, bottom wall. So everything is here and it says 6 faces. So that's all we wanted. And all the points are here. Okay. Now we can close this and get back to our meshing procedure. So just like how we have SnappyHex mesh dict, we also have something called mesh dict for this one. So there are many templates from your cfMesh installation. So if you go to your cfMesh installation folder, you can find a tutorials folder, and if you go inside this and search for mesh dict, you'll be getting a lot of templates that you could use. So I just made this file out of these templates just to mesh this one. So I'm going to copy that mesh dict and then paste it in my system folder. Now let's try to understand what is there inside this mesh data. Okay. So first of all, I'm just going to comment these things entirely. Okay. Now just assume that only these two lines are there. Everything else is a comment. So we are saying that this object is a mesh dict and it's part of the location system and its dictionary file, and the surface file is formula.fms. It has to be within the quotes. Okay, and then we also have to define the maximum cell size. So let's start with one basically, and if I go here, the way to do the meshing is Cartesian mesh. So just type Cartesian mesh, press enter, and the mesh will start. So if you open your task manager while this is running and then go to your performance CPU, right click, change graph to logical processor, you can see that it is actually utilizing all the cores. You don't have to do decomposition, you don't have to specify how many cores to use. None of that is necessary. It will by default take all your cores and then do parallel meshing. Now the meshing is over. So you can drag and drop your para.foam file, apply. Yeah, now we got our mesh file and you can see that there is no car. It just looks like there is something there, but there is no car. It is because of the cell size. It will not fail the mesh. Instead, it will just try to put whatever is possible for the meshing algorithm. So we have to understand how this is working. So right now we have the maximum cell size as 1, and that's why it was not able to do. So I'm just going to make it as 0.5. Let's take half of it. Go here and run the mesh. So as the size of the mesh goes down, the speed of the uh, meshing process will also go down. And now you can see that it looks slightly better. Nothing like an F1 car, but you get the idea. The lower the cell size, the better the feature is. So just for one more trial, let's go to point 1, save the file, run it again and wait for it to end. It might take a bit more time. It is over, so you can go here, hit refresh. and you can see now it's much better, definitely much better. Okay, so if you just go and then choose formula, or else let's open one more paraview file and then choose only the formula, apply. Okay, hide this. Yeah, you can see it now looks like a formula car, maybe totally messed up, but looks like a formula car. So now you understand the point. If you reduce the maximum cell size, you will get better results. But you also have a lot of cells now in the overall domain. It gets smaller and smaller. Even in the region where there is a free stream, you have a lot of cells. So what we are going to do is, like, we are going to keep this as 0.7 only, save it, and then you will run the Cartesian mesh again, just to understand what the size of the mesh is going to be. Okay, it's over. Okay, now I think this size is okay for the free stream. Maybe for a tutorial it's okay. If you're working on validation, this might not be okay. You might have to go smaller. And as you can see, my RAM is also only 24 GB, so I'll try to keep it to that level. If you want even finer mesh, you can learn the procedure and go on and then do it as you wish. Okay, now what we are going to do is, like, add local refinements specific to this formula patch. So if you remember from the STL file, that patch is called formula. If you have any doubts, you can just open this geometry.stl near VS Code, and you can see that the name is formula. Okay. Now we are going to create a local refinement. So I can just type local refinement, open brackets, and here I'm going to enter formula dot star. Okay. So that's formula is the name, and whatever starts with formula. You can even just put formula, but I like it to use this way. And then open brackets, then you can define your cell size. Give a space and then you can define a cell size. So let's put 0.1 because that was the previous size that we used. Let's go here, run our Cartesian mesh. Okay, the meshing is over. So hit refresh. You can see that the outer cell size is remaining the same, but the inner part is definitely refined. Yeah, it is like the previous time. Now what we are going to do is, we are going to refine the lower wall as well, because in aerodynamics, especially for an F1 car, the flow below the car is also very important. So we are going to refine the lower wall as well. So you can just copy this block, paste it in this way, and then you can put that specific name. So in my case, it's called bottom wall. As you can see in my block mesh, I have defined it as bottom wall. So I'm just taking that name here and then defining the same size as this, or maybe slightly bigger you can put if you want, but the same size also works. So I'm just going to put the same name, same size, and then run the mesh. Okay, the meshing is over. You go here, hit refresh. You can see now the lower wall is also well refined. Okay, now it's time to create a refinement box. So if you take a slice and then click apply, and maybe go to surface with edges, you can see that the mesh is quite bad. Remove the triangulate the slice. Okay, now you can see that near the wake region, it's pretty bad and the cells are very big. So we have to create a local refinement region. So what we are going to do here now is, you go to the mesh depth, and just like how you created this local refinement, we have to create something called the object refinements. Okay, so I'm just going to copy this block, then paste it here. And this object refinement is like this syntax. So cell size, and then you put cell size specific to that. Let's say I just want it to be 0.1, whatever that box is going to cover. It's going to be something like this, and whatever within that box, whatever cells fall within that box will be considered as cell size of 0.1. But for tutorial purpose, let's keep it as 0.3 or 0.35, and we have to define the center of the box and then the length in x, y, and z, and you have to give the type as box. So this is going to create a box, a virtual box, and then refine whatever cells fall within the box, and then it will remove box. So it's like it will not be a patch kind of thing. It will be just a refinement definition. So once you define that, you can go here and again run the mesh. So the meshing is over. Again, we can go here and just press refresh. Yeah, you can see just this box got refined, and this almost remains the same because of the cell size, and this is also going to remain the same. Okay. Now there is one more thing that we can do, add boundary layers, because as you might know, there will be space between the car and the ground. It's not like completely touching, so there must be some cells in between them, but it is getting lost because of the cell size. So we are going to add boundary layers for the lower wall, which is the bottom wall, and the formula car. So the syntax is you just first call boundary layers and then brackets, and you have to mention patch boundary layers. So any name can be there for that matter. And then I'm just going to mention my formula as well as the bottom wall. So we can define the number of layers, the thickness ratio, and usually we keep it 1.2, even 1. Sometimes people keep 1, but usually 1.2. This is like the growth rate, and then the maximum first layer thickness and the allow discontinuity. So we are just going to keep it as 0. And there is also one more thing that we can do, which is the optimize layer. So we have to put it outside this group of layers. Just save the file and then run it. Okay, the machine is over, so go here, refresh. Yeah, now there is layers, but still it's not creating the walls underneath, which means the cell size has to be smaller because it's not able to capture it properly. So you can try to do it with lower cells because it's going to take a lot of time, but eventually you understand the overall idea of how we are meshing and everything. So I'm just going to show the mesh where it was able to do it. So I ran it already. This is with even finer cells, and you can see that it was able to capture the lower part. So these are the values that I actually used. So the maximum cell size was 0.5, and the cell size for the formula is 0.05, bottom wall was 0.06, and layers were 5 with thickness ratio 1.2, and the cell size within the refinement box was zero point 0.1. So these are the values I used to create this mesh. Actually, the outer mesh can even be smaller, but since I have limitation of number of cores and the RAM, so I was able to create only this much. It's still not a great mesh. We can work on it, but my STL also has some problems like non-manifold geometry and everything. So to check whether your mesh is good or not, like you can see, it shows a lot of warnings. Error in phase pyramid, 41 faces pointing in the wrong way. So these are because of non-manifold faces. To check whether your STL has a problem or not, you can do this surface check followed by your STL name and you press enter. Let's see it one by one. Surface has no illegal triangles. Okay, good. And checking points between found 8 nearby points, and it says surface is not closed since not all edges connected to the two faces. So there are problems within the geometry. It should be a closed geometry, and it also says it is splitting the unconnected zones into parts, and you can find it in those obj files. Yeah, it will be created here. So you can see along with our STL, we also have these VTP files. So if you open them and see, this is the VTP that comes after checking. If I open all the OBJ files, you have to do it one by one. So you can see they are coming as the different parts. It's not able to recognize them as a single part, and these are unconnected parts, and these are problems in STL. So you can safely delete these files, it's not needed. So this is how you will check whether your geometry is good or not. Like for example, if I just run it on my boundary.stl, you can see that the surface is closed, all edges connected to two faces, number of unconnected parts just one, and there are no obj files that was formed. it comes only when there is a problem. So it also says surface has no illegal triangles. So this is a good output for the surface check. But if it comes like previous the formula check, then it's a problem. Then your mesh will also not be very good. So you have to take care of that while you are doing the mesh in your cfMesh. So this was our final output, and I'll also show the geometry. Yeah, so this was the final output, and if you want, you can actually run the simulation on this. But since this is not a great mesh, you can't expect great results. So you can also run check mesh. It's going to be very problematic, especially because the cell size is too big. Yeah, I can see it's failing 5 mesh checks. Usually skewness fail is okay, but non-orthogonality, zero volume cells are going to be a big problem when you actually run the mesh. Oh, sorry, run the simulation. So you have to first fix your STL using FreeCAD or anything. But since this was downloaded, I don't have much say on the cleanup of the STL. So this was the original STL, and you can see it still has a lot of problematic faces. So you can try out with a good geometry. Maybe you can try other geometries from Fetch CFD and then try to run the mesh. And if you get a good mesh, post it in LinkedIn, and don't forget to tag Codynamics. We'll be happy to reshare and share the happiness with you. So if you have any specific doubts related to cfMesh or OpenFOAM or CFD in general, you can drop it down in the comment section. Subscribe and consider dropping a like to the video if you enjoyed it so far, and share it with people who might benefit from this video. Hoping to see you in the next video. Until then, happy learning.